heard about stacks and queues and feel like you're supposed to know more about them. Or you might know about them, but be unsure about why you need to know. Either way, I want to show you all the things there are to know about stacks and queues, and hopefully you'll find them as interesting as I do. Chances are you've run into something that's sounded really scary and had an error message that said something like, stack level too deep. Well, it turns out that the stack in those error messages are really just a data structure. Whenever you see error messages about the call stack, that's usually referring to another type of data structure called a stack. A stack is a linear data structure that's not too different from a linked list. They also have an order and sequence to them. The unique thing about stacks, however, is that their order and the way that you traverse them starts from bottom to top. Stacks are often implemented using linked lists. And if you know a little bit about linked lists, then you can use that as a foundation for thinking about how stacks work. So here we have a stack of elements. The element on the bottom is at the bottom of the stack. The element at the top is what we call the top of the stack. Now let's say that we wanted to add another element to our stack. There's only one place that we could add it. We could only add it to the top of the stack. And what if we wanted to remove an item from our stack? Well, we have to remove only what's accessible to us at the top, which means we'd have to remove the item at the top of the stack. A good rule of thumb when dealing with stacks is that you can only ever insert or delete whatever is at the top of the stack. If this reminds you a little bit of linked lists, well, that's a good thing, because linked lists are often implemented or often used to implement stacks. Usually, a singly linked list is a great under-the-hood implementation of things that we use for stacks, like the call stack. Stacks operate according to something called the LIFO principle. LIFO, L-I-F-O, stands for last in, first out. The last element that was inserted into the stack is the first element that's going to be removed. You might also hear the term phyllo, which stands for first in, last out. It's basically the opposite of what I just explained. The first element, the one at the bottom of the stack, is always going to be the last one to be removed, since you have to remove all of the elements that are above it first. So we know that singly linked lists are often used under the hood to implement a stack. But there's another reason why singly linked lists work so well. We know that stacks only grow in one direction. They only grow up. But basically, what's going on is that we're adding and removing elements from only one place in the stack. This is actually something that linked lists are really good at. If you remember learning about linked lists, then you know that inserting and deleting from one space in the linked list can be really efficient. In fact, you can do it in constant time. This is why singly linked lists are a great implementation and a good technique for actually creating a stack data structure. Linked lists aren't the only option for implementing a stack. We could use an array too. But arrays have a couple drawbacks. The first is that an array is a static data structure. That means that you need to know how much space the array is going to need ahead of time. Our stack has 6 elements in it, so we can allocate an array of 6 items. But what if we wanted to add something to the top of the stack? We've only allocated space for 6 items, which means that we're going to try to add something where there's no space. This is what we also refer to as a stack overflow. And it can be pretty problematic because as soon as you run out of memory, everything kind of breaks when you want to add another element at least. Since linked lists are a dynamic data structure, this isn't really an issue. We can add a new element at any point in memory that's free. It doesn't have to be all the memory allocated together. Okay, so we've allocated 6 elements that are currently in our stack. Remember that in a linked list, every item or every node in the linked list that you add doesn't have to be consecutive. So the same goes with our stack when we're using a linked list under the hood. When we add something to the top of our stack, it could be at any point in memory, which means that our stack can grow in size as necessary, as long as we're not completely out of system memory in the process, which rarely happens. We were able to insert an element to the top of our stack at any free point in memory that we could find. And this is where linked lists, especially singly linked lists, are a perfect tool for implementing stacks. There are a couple functions that we'll see a lot when we're dealing with stacks. 2 of them are called push and pop, and they basically are how you interact with a stack. If we wanted to add this element right here to the top of our stack, we could call the push function, which will be what we use to insert this element into the stack. And now, what if we wanted to remove that same element from the top of our stack? We could call on our pop function, which is what we use to delete elements from the stack. There are 2 other functions that we also might see. One of them is called peek, which allows you to look at the first element on the top of the stack without looking at anything else. Another one is empty, which basically just tells you if the stack is empty or not. The only other really handy function that most stack implementations will have is a method called size, which will tell you how many elements are on the stack at any given time. This can be particularly helpful if you're dealing with manipulating and adding and removing data from the stack, and you need to know how many elements are already on it to begin with. If you've ever dealt with undo or redo in a document or in some sort of editor, what you were really doing was dealing with items on a stack. Whenever you perform an action, you add an element to the stack, and whenever you Control-Z and undo it, you pop that off the stack. It's a similar scenario with your browser history too. If you navigate to a website, click on a link and go elsewhere, and then navigate back, the states of your browser history are really just states preserved in a stack. If you want to pull back the curtain on abstractions of stacks even further, you can take a look at the Mozilla Developer Network's API for the history object. If you take a look at the JavaScript history object in your browser, you'll actually see that there are methods like push state, replace state, pop state that you can call to change your browser history. If those methods sound like methods that should be called on a stack, that's because that's exactly what they are. My personal favorite example of a stack in the wild is the call stack. When it doesn't overflow and you don't get a crazy error, there are actually pretty interesting things going on with how the call stack is built up. Even with a single function call, so many elements and items are being added to a stack. You just don't always know that it's happening, but it is. No matter what programming language you use, you've probably worked with something that looks a little bit like this. Some sort of function call. Usually, most functions will call other functions from within them. But let's unpack what's actually going on when this function is called. Here, we'll see the function definition for the outer function. We can see that it declares some local variables, and maybe it does something with those variables inside of that method call. And it calls out to another function and passes an argument to it. If we look at that middle function, we'll see that it takes some arguments, creates a local variable, and calls out to an inner function. If we take a look at the inner function, we'll see that it takes in some arguments and returns a value. So what's actually going on with all of these functions? Well, we have 3 different procedures that need to happen. As these procedures execute, we're actually building up a call stack of all of these little pieces of code. Each procedure corresponds to an element in the stack. When procedure 1 runs, in this case, the outer function, it allocates some of its memory for whatever local variables it creates. And it also allocates some memory for its return address. This whole section of code, the whole section of memory that is allocated to the outermost function, is referred to as a stack frame. Since the outer function is the first one to execute, it is the first stack frame that is added to the stack, which is what we can see right here. It's a similar story for our middle function. It allocates space for whatever local variables it needs and its return address, and this entire procedure as a section of memory is allocated as a stack frame. Notice how we're keeping with the rules of a stack. We're only adding each stack frame to the top of the stack. If we remember the principles of last in, first out, then we know that procedure 1 is going to be the last element that will be removed, since it was the first one that was added to the stack. This process will continue again with our third procedure. After it allocates whatever memory it needs to, it's added to the top of the stack as a stack frame. What we've been doing as a part of this function call has really just been building up a stack with stack frame elements. So what happens when this procedure, our innermost function, finishes running? Well, we need to tear down the stack. Since procedure 3 is at the top of the stack, when it finishes running, its stack frame will have to be, according to the last in, first out principle, be popped off. This process repeats again for the next procedure that's on the top of the stack. When it finishes running and has a return value, it can be popped off the stack. At the bottom of our stack is the stack frame for our original procedure. Now that we've finished running and executing the entire procedure and all of its inner functions, all we need to do is take its return value and pop this off the stack as well. Every single function call, no matter how simple it is really just stacks of procedures being pushed and popped off. When you start thinking about some of the most complex programs that you've dealt with, all of the different processes that that program does is really just handled with a stack data structure. But sometimes stacks aren't quite the right tool for the job. And that's where queues can sometimes come in handy. Stacks and queues are often taught together because they're almost like opposites of one another. They can be built up and structured in similar ways, but they follow 2 very different principles. So let's look at when a queue might be a better option for us. Queues aren't too different from the other linear data types that we've looked at so far. Because they're linear, there's a concept of traversing them sequentially. Here is a queue with 4 elements inside of it. Remember that the size of the queue could be very long, but in this case, we have only 4 items. Let's say we wanted to add an item to this queue. The process of adding an element to a queue is known as enqueuing. So let's go ahead and enqueue this blue element to our already created queue. Now that we've added an element to our queue, how do we go about removing something from it? We can use a process called dequeuing. When you dequeue an element, you remove it from the front of the queue. If we wanted to dequeue something from our example queue here, we would have to dequeue whatever's at the front of our queue. You might notice something interesting happening here that we haven't really seen before. When we inqueued an item, we added it to one end of the queue, but when we dequeued an item, we didn't remove the item we just added. We removed the one at the opposite end. This is a fundamental part of how queues work, and it turns out there's a name and a principle that queues follow that makes this rule easy to remember. So here we have our queue again. But let's be a little more obvious about the different parts of this queue. Every queue will have a front and a back. In this case, this red element is the front of our queue, and this blue element is the end of our queue. Whenever we want to remove something from our queue or dequeue it, we have to do it from the front. Similarly, whenever we want to add something to our queue or inqueue it, we have to do that from the end of our queue. The fact that we have to dequeue from the front of our queue and inqueue from the back of our queue is also known as the FIFO principle. FIFO stands for first in, first out. Even though stacks and queues are different, you will notice that some of the functionality feels very similar. The push function on a stack is very similar to a queue's inqueue function. A stack's pop function is very similar to a queue's dequeue function. Stacks also usually have functions like size or is empty. Queues, you will find, will also have their own implementations that will be very similar and usually will be named exactly the same. There's another reason that stacks and queues seem so closely intertwined. That's because you can implement both of them using either an array or a linked list. We know how arrays and linked lists might be better or worse for a stack. So how do those two options compare for a queue? We know that arrays can be a great implementation when we know the size of a data structure ahead of time. There are many instances, especially with queues, when we don't know how big our queue is going to get. So what happens when we want to enqueue an element, but we've run out of allocated memory and space? Well, what we have to do is copy over the contents of our array implementation of our queue and then enqueue our new element to the end of the queue. When we run out of memory in our array implementation, we have to do a couple things. Copy over all the contents of our array, allocate more memory than we previously had, and then enqueue our element to the back of our queue. But there's another added complexity with array-based queue implementations. We need to be able to enqueue from the back of the queue, but also dequeue from the front. What makes this tricky is that we're dealing with elements on either end of our structure. It was a bit simpler with stacks, where the pushing and the popping happened in one place. But with a queue, you really have to concern yourself with the front and the back anytime you want to insert or remove an element. The trouble with this is that as our array grows in size, we'll need to be able to access both ends. And for a larger array, the space and time complexity of accessing two ends of the structure is going to get more and more complicated as our input changes. Another reason that arrays can be a poor choice for queues is that you usually don't know how many elements are going to be in your queue, which means you'll probably end up copying over and reallocating memory way more often than you'd like. But there is one data structure that lends itself really well to problems where you don't know how much memory or space you might need. I'm talking, of course, about our dear old friend, the linked list. Linked lists can grow dynamically in size, which means that if we wanted to enqueue an element or many elements or dequeue elements, it wouldn't be too tricky to do that. So how could we implement the enqueuing of this same element in a linked list implementation of our queue? We need to enqueue this item to the back of our queue. Since we want to be able to enqueue this element, all we need to do is find a free space in memory anywhere that it's available and make sure that we set the pointer of our linked list correctly. We can find a free spot and enqueue an element to the back of our queue. And what if we wanted to dequeue an element later on? All we'd need to do is free up that space in memory and change a couple of pointers in our linked list implementation of our queue. Another reason that linked lists can be preferential for implementing a queue is that keeping track of the back and the front of the queue just involves keeping two pointers or two references in memory. It's easier than arrays, where as the array grows in size, the complexity of keeping track of the front and the back of the queue gets trickier and trickier. With a linked list, as long as you know the reference and the pointer to the node that is the front of the queue and the back of the queue, you almost don't need to worry about the size of the queue as it changes, as it grows or shrinks. Since all we're doing is keeping reference to the front and the back of the queue, it doesn't matter how big the queue is, it will always take us constant or O1 time to perform an enqueue or dequeue operation. So now that we know how queues work and what makes them different from stacks, there's one important question left to answer. Why should we care? Well, as it turns out, queues, like stacks, are everywhere. If you've ever worked with a backend developer or had to write backend code, then you know that on the server side, you usually have to deal with things like workers or scheduling jobs or handling tasks. All of these, in some way or shape or form, use a queue data structure to implement everything that they do. A very common example of this is a job scheduler. Job schedulers will usually spin up a separate thread and handle whatever jobs or workers or tasks are sent to it. The way that they do this is by taking the first job that is scheduled and enqueuing it, and as more jobs come in, enqueuing those. Of course, since queues operate according to the FIFO principle, the first job that is received by the job scheduler is the first one that will be processed and the first one that will be dequeued. A job scheduler handles the enqueuing and processing of these jobs until the entire list of jobs is completed and the queue is empty. But it's not just backend code that uses a queue under the hood. If you've ever worked with front-end code, specifically with jQuery or jQuery's API, you've actually interacted with a queue, whether you know it or not. The jQuery API uses functions that can be executed asynchronously, and it takes those functions and creates a queue of steps that will be called on the CSS values that are transformed. If you look at their API, you'll notice that there's actually a dequeue function that you can call that allows you to move from one element to the next. We also interact with queues not just as creators of technology, but as consumers of it too. The machine that you write your code on, or just check your email on, uses a queue to handle and process all of the tasks that it has to do at any given time. On most machines, this is implemented as a multi-level priority queue, which is basically a queue that schedules different tasks based on how important they are. For example, in your own machine, you might have system processes, interactive processes, background processes, and maybe even batch processes. The ones that are generally the most important are system processes. They take precedence over things that need to happen in the background, so they have a higher priority. The way that your system processes all of these jobs is based on their priority and order. Jobs can be sorted by priority, and multiple queues can enqueue jobs that are ready to execute whenever the higher priority items have finished running. You can also have multiple levels of queues on your machine based on how important they are. Whenever you make a web request, a server has to handle and process not just your request, but every single other person who's also making a request to the same application that you are. Servers handle all of the requests that they get at any given time by something called request queuing, which, you guessed it, uses a queue. For example, if 3 different individuals are trying to access one application, one website, hosted by a single server, all of their requests might reach that server at nearly the same time. The server will handle all of those incoming requests by enqueuing them one by one. This is something called an incoming request queue. One by one, the requests that came in will be processed. And they will, of course, be processed according to the principle that all queues follow, with the first item in the queue being processed first, and the last item at the back of the queue being processed last. This is something called the processing request queue. The server handles all of the requests that came in the order that they came in, serving the first request that came in first. Once it handles each request at a time, it takes those requests and enqueues the responses to be sent out, again, in the order that they came. The first request to come in this case, the green request, was the first one to be enqueued. It was at the front of the incoming request queue, so it's the first one that will be processed. Request queuing is part of the request lifecycle after it's been sent to an application, but hasn't been processed or entered into a system yet. Every single web request is enqueued, processed, dequeued, and sent back as a response. So queues are really everywhere, and we interact with them all the time. I hope you understand and have a better appreciation for stacks and queues now. Check out the rest of my articles and videos at dev2/Vaidehi Joshi. Thank you for watching.